Chapter 3 of Informing Business provides the most significant theoretical grounding for the rest of the book. And specifically, it deals with the notion of what constitutes complexity, the concept of fitness, and finally, it looks at the question of what constitutes theory and when is theory particularly useful and when is theory less useful. Let me start out by saying right off the bat that complexity is messy and there's nothing we can do about it. My argument, and I have studied complexity extensively over the years, is that the source of this problem, or this messiness, is the fact that complexity derives from three distinct sources, and it's almost impossible to use the term without confusing them. The first of these sources is what we experience. This is complexity as we feel it in our head. The second source is the external environment. Certain environments are very turbulent. We call these complex environments. Certain environments are hard to figure out. This is an objective phenomenon, but nevertheless, it's easy to confuse how we feel about the environment with the way the environment actually is. Finally, in the middle, we have how we represent this environment in terms of rules and symbols and so forth. And this is really important because if we are going to do very large tasks, we need to use these symbols because we can use symbols to store information and recall it. For example, writing it down on paper. We need symbols if we're going to communicate between ourselves. So if the problem involves more than one person, we're going to need these symbols. And finally, we use symbolic activities to act. For example, pressing keys on a computer, and we observe the consequences. For example, what displays on the computer in symbolic terms. So this middle area of the problem space is very, very important as we try to solve complex problems. But each of these areas has its own form of complexity, and as I said at the outset, it's almost impossible not to confuse them. So we'll talk about each of these three areas of complexity individually now, and we'll start with experienced complexity. And experience complexity is almost entirely driven by unfamiliarity. And when we encounter unfamiliarity, we perceive the task to be difficult. We often experience uncertainty, the question of what to do next. And we frequently deal with ambiguity. Is this a man playing a saxophone, or is this the face of a woman? And as we become more and more familiar with the task, all of these things decline. The task itself may not have changed, but how we experience them changes. So when we use complexity as a synonym for difficulty, uncertainty, or ambiguity, what we're really dealing with is unfamiliarity. The next form of complexity is the complexity of how we represent things symbolically, either with letters or images. And this is what we know as problem space complexity. Now, to illustrate problem space complexity, consider the following map of Manhattan. And if you look at Manhattan, this particular region of Manhattan is laid out in a grid, which means that if you're given a street number and an avenue number, it's very, very easy to come up with rules that take you from some arbitrary starting point to some completion point. And so when we want to represent directions in Manhattan, it's relatively straightforward by virtue of the fact that it's laid out in a grid. Now, compare this with Boston. And this is downtown Boston. The rumor, and I don't know whether this is true or not, is that the streets in Boston were basically laid out according to cow paths. And apparently cows don't like moving in any regular direction. And as a consequence, if you wanted to create arbitrary directions between some point A and point B in Boston, you would find yourself dealing with a much, much larger set of directions. And I grew up in Boston, and what I will tell you is when you ask someone for directions in Boston, you never get them. And it's not that they are necessarily hostile, some may be, but not necessarily, but rather it's the problem of the directions are extremely complicated. And that complication, the number of alternative paths, the difficulty describing the paths and so forth, is what drives problem space complexity. There are a number of implications of complications or complicatedness in the problem space. For example, if you take a look at the problem space, the descriptions of protocols tend to be quite lengthy. So the last page of Dodd-Frank is like page 2319, and that's just the description of the regulations that need to be created as opposed to the regulations themselves. If you look at Obamacare, it was a stack in the early days of Obamacare dealing with the regulations. Here's the layout for trying to decide what version of SAP to develop. And so forth. So as a consequence, you tend to have lengthy protocols. It tends to take a long time to learn them. That is, of course, a function of length as well as the complicatedness, the number of paths through them. And it also increases the likelihood that you will encounter errors along the way because with all these paths to choose from, the possibility of accidentally stepping on a wrong path is high. So long protocols, long time to learn, and likelihood of error is a function of the complicatedness of a system. When we deal with real-world complexity, we hear the same three sources over and over again. The number of attributes in a system, the degree to which they interact, and the rate at which the relationships between them changes. Now, there are two typical outcomes associated with real-world complexity. One is turbulence, which is easy to explain, and the other is ruggedness, which takes a lot more time to explain and will be the focus of a lot of what we're talking about here and what we talk about later in the book. As I mentioned, turbulence is relatively easy to explain. It's a little bit like volatility, but whereas volatility tends to exhibit a kind of random pattern, turbulence tends to exhibit patterns where things behave in an orderly way for a while, and then all of a sudden, in a very short period of time, they seem to go out of control, and then maybe they go back to a more orderly period. And this is sometimes referred to as punctuated equilibrium, this mixture of order and highly volatile behaviors. We see this, for example, in many of the financial markets, such as the stock market. And it makes it really challenging because when you have orderly periods of behavior, you can come up with rules and do very well on them, but then all of a sudden these shocks occur. And when these shocks occur, you find that your rules frequently have to go out the window, and after the shock is over, sometimes things revert to the previous behaviors, and sometimes they don't. Unlike turbulence, fitness takes a while to get your head around. And let's look at it in the context of what we've already talked about. When we talk about experienced complexity, we're dealing with unfamiliarity, and unfamiliarity is mainly a function of the context. If you've never seen the context before, then you experience this sense of difficulty and uncertainty. And if you see the same context over and over again, that unfamiliarity declines. Now, problem space complexity, on the other hand, is really a function of the protocol that you're using to perform the task. In a certain sense, if you ask the question, how long is the computer program that we would need to solve this particular problem, that gives you a good sense of the problem space complexity. If the program is very small, it means that there aren't a lot of variables you need to consider and there aren't a lot of decisions to be made. If the protocol is very large, or the description of the protocol is very large, that suggests that you have a high level of complicatedness. So if you look at the regulations for Dodd-Frank, or if you look at the rules for Obamacare, what we're saying is those are very complicated because the protocol is very, very long. Now, when we talk about fitness, what we're really asking is, if we have a particular protocol in a particular context, how well does it fit? So it's sort of the intersection of protocol and context. It's very, very specific. And this notion of how well something fits is the key to fitness. Now, when we talk about a high fitness, what we mean is that if we were to encounter that same context again, there is a very good chance that we'd want to apply the same protocol. Low fitness means that if we were to encounter a similar context, we'd look for some other protocol because we didn't feel the protocol was a good fit. This is very close to the notion of reproduction in biology, and that's really where the term fitness and fitness landscape came from. Another aspect of the high fitness protocols is that other will imitate it. So Stradivarius developed a marvelous protocol for developing violins, for making violins. What happens? Lots and lots of people tried to imitate what he was doing. Now, one drawback of fitness is that it is virtually impossible to know in any real-world situation. The only way to really judge fitness is after the fact to see how well a particular protocol, for example, has reproduced. But on the other hand, you can use fitness in a conceptual way that's fairly useful. And we refer to this as a fitness landscape. And so we begin by saying that fitness is a function of a particular protocol and a particular context. So it's basically, and each protocol could be described in terms of a series of attributes, and presumably each context could be described in terms of a series of attributes. Now, the fitness landscape essentially is a visualization of fitness across all possible protocols and concepts. So it basically becomes like a graphic of fitness across all possible combinations. So there are two basic types of landscapes, or rather there's a continuum with two extremes. A decomposable fitness function means that if you have all the attributes, say there are 6 attributes that determine protocol and context, obviously that would be very, very simple. Typically there'd be hundreds, if not thousands. But for our purposes, let's just imagine there are 6 of them. If each one contributes to fitness separately, then that becomes very, very simple. Suppose each one has 2 values. If its value is 0, it does not contribute to fitness. If its value is non-zero, we'll say 1, then it contributes a certain amount to fitness, like x3 contributes this amount to fitness in the graphic. So under those circumstances, you can look at each attribute separately, and it's meaningful to ask a question, how much does x5 contribute to fitness? And you could turn that into a hypothesis, and you could do statistical tests to determine the range of possible contributions for x5 to fitness across a landscape. Now, at the other extreme, our landscape may be interacting, which is to say individual contributions cannot really be separated out. A particular change in value, say x1 changes from one value to another can have a big impact on fitness, but it won't always have the same impact. And I'll talk about later how a good example of this is a recipe. Sometimes a very small ingredient can have a major impact. For example, if you leave baking powder out of a cake, you start baking construction material instead of a cake because it won't rise. And yet, when we think about baking a cake, the quality of the baking powder is probably one of the last things that we would think about. But it's really hard to determine what fraction of fitness is determined by the sugar and what fraction of fitness is determined by the flour, because in a recipe the ingredients interact and essentially all of the ingredients are needed. Whereas in a decomposable landscape, you would be able to actually identify what percentage of fitness is the result of each of the different ingredients. Now, the reason this is significant is because when you think about landscapes qualitatively, interacting versus decomposable variables produce very, very different conceptual pictures. So if we take a look at a decomposable landscape where each value contributes a certain amount to fitness, there is going to be a peak fitness, which is simply the maximum value for each variable added together. And so essentially, if you are operating on such a landscape, it's very easy to reach the top because you just test out each variable individually, choose the better value, and when you have the best value of all your variables, you're up there at the peak. Now, when you have interacting variables, on the other hand, you have an entirely different type of landscape because there is no such regularity there. So a rugged landscape is one with many peaks and often very, very sharp drop-offs. In the pyramid, you don't have the sharp drop-offs because each variable is limited to its influence. That's not the case where there's interaction. Sometimes a very small change, such as not putting baking powder in a cake, will lead to a big change in the resulting fitness. So what this means is if you are operating on such a landscape, you are looking for combinations of attributes to a product or combinations of marketing channels, you may find yourself in a situation where any incremental change produces a decline in fitness. That's what we call a peak. Yet there may be other people on much higher peaks, but the only way to get to them is by going through changes that take you into the valleys before you move up to the peak. And this is why this visualization of the landscape is very important. So rugged landscapes, as I say, have many local peaks and very sharp drop-offs between peaks. So let's take a simple example and consider how the questions in a test differ from the recipe. So now if you've got a test like the SAT, each answer adds to fitness independently. In other words, your score consists of the points for the number of right answers, perhaps minus the points for the number of wrong answers. And each question has a right answer or a wrong answer, and you always do better on your overall score by getting the answer to a particular question right as opposed to getting it wrong. Now, returning to our recipe example, fitness is determined by the combination of attributes. And there are many high fitness combinations. In fact, if you look at a cookbook is really a collection of what the author perceives as local peaks, which is to say, if the author perceived you could improve a recipe by, say, increasing the amount of vanilla, then they simply would have added more vanilla to the recipe. So each recipe in a cookbook is a local peak. But if you try and ask a question about a particular attribute, say the ingredient garlic, you can't really give an answer to the question, is this a good or a bad ingredient? Because garlic is probably a good ingredient in 95% of the recipes involving lamb, and it is probably a bad ingredient in 95% of your typical dessert recipes. Now, there is, in fact, in San Francisco, a restaurant called the Stinking Rose, where every recipe has garlic. And what I would say is the appetizers and entrees are really good there. I'd steer clear of the desserts. Now, ruggedness is important because there are some very significant implications of operating on a rugged landscape that are different from operating on a decomposable landscape. For example, on a rugged landscape, different approaches to fitness succeed, so that there is no right answer to a problem. Different approaches can deal with different outcomes. So if you look at the restaurant industry, for example, there are lots of different types of restaurants that are successful. There is no universal formula to restaurants. Another aspect of it is inconsistent changes to fitness result when variables are changed in different contexts. What this means is that sometimes a little change will have a big impact and sometimes it won't have any impact at all. There is no universal theory as to raising or lowering prices, because sometimes when you raise price it works for you, sometimes when you lower price it works for you. It depends upon the context. If you have ruggedness in a landscape, it's going to tend to produce inconsistent research findings. We'll talk about this later when we talk about Chapter 10 and replication, but the fact is that different research findings often occur when similar problems are being studied. That is a natural consequence of ruggedness, because on different peaks, different rules operate. Sometimes little changes make a big difference in fitness. This, once again, is another characteristic of ruggedness. On a decomposable landscape, little changes tend to produce little results. On a decomposable landscape, things are nice and orderly. But when you get to a rugged landscape, sometimes little things make a big difference. And finally, or almost finally, there's the stickiness of entities. If entities migrate to local peaks, then they're typically not going to want to leave those peaks, because doing so requires going through a valley. So it becomes very, very challenging to manage change if we actually want change to occur on a rugged landscape. On a decomposable landscape, that's not nearly as much the case, because on a decomposable landscape, every change will incrementally move you up if it's the right type of change. So you're going to be very interested in what other people are doing to make themselves successful, because the same steps will make you successful. Finally, turbulent dynamics. When you have rugged landscapes, what tends to happen is, as the peaks rise and fall, you will frequently end up experiencing periods where there's very little change. Everybody is existing on their peaks, but then all of a sudden you get a mass migration from one peak to another as a peak declines. And so as a result, what you often find is periods of order followed by short periods of rapid change when the entities on the landscape reorganize themselves. So when you see these characteristics in a landscape, there's probably a good chance that you're dealing with rugged landscapes. If you don't see these characteristics in a landscape that you're dealing with, then you may be able to treat it as much more of a decomposable, orderly landscape. As I mentioned a few slides back, one of the challenges of fitness is that it is essentially unknowable. And as a consequence, while we always seek to achieve fitness, we never actually know what fitness is going to be. So as a consequence, we need to try to estimate it. And practically every measure that we take in business, or really almost anything else where we measure, is intended to be an estimate of fitness. Here what we have is the balanced scorecard, which is a very complicated estimate of fitness involving the financial perspective, the customer perspective, innovation and learning, internal business perspective, and so forth. Other estimates of fitness are much simpler. Did your stock price rise? How much money do you make? All of these things are ways of estimating fitness, and estimates of fitness can have an important role because, in a sense, they can be self-fulfilling prophecies. If an estimate of fitness is widely expected, then we use that estimate to determine whether or not we think we're on a peak, and that estimate can drive a lot of behavior. As I mentioned, one of the problems of estimates of fitness is that they're not necessarily all that good. And so let's just take a specific example of college rankings as done by organizations such as U.S. News and World Report. Well, how do they create those rankings? Well, essentially, they use a kind of a decomposable model. So what happens is you get points for having a whole bunch of different majors. You get points for having lots of extracurricular activities. You have points for the number of athletic facilities that you offer and how well your teams are doing and so forth. And using this complicated formula, they come up with a ranking. And then to that ranking, they add the academic difficulty, which is to say how hard it is to get in. Well, this is a ranking that tends to drive a lot of students to apply to particular universities. But when you think about it, it's a terrible measure of fit for an individual student, because most students are not interested in majoring in every single major. They're not interested in every extracurricular. They're certainly not going to participate in every sport. And they can't get into the top-ranked universities in most cases. In fact, I would say that there might be 2 or 3 people in the whole world for whom college rankings are actually a good estimate of fitness, because they can't decide on their major. They're interested in everything. They love all sports, and they can get in anywhere because they're such strong students. There just aren't a lot of those folks around. So in a certain sense, it's a terrible estimate for most individuals, and yet it drives a lot of behavior because, terrible estimate though it is, we don't have any better estimate. And this is one of the interesting challenges of estimates of fitness, and something that I'll return to a number of times as we move into later chapters. So let's think about how we might take the question, why are estimates of fitness important, and turn that into a series of research hypotheses. So, hypothesis 1, they can guide us on rugged landscapes. How would we test this? Well, we'd try to assess the ruggedness of a particular landscape and then perhaps interview decision makers to determine how much they were guided by various estimates of outcome that they were seeking to achieve. They can define our dominant fitness peak. Perhaps we could study to see whether individuals who have a particularly strong estimate of fitness are less likely to try different things than someone who's got a weaker estimate of fitness and therefore is not as attached to a peak. They provide us with a means of affecting behavior. We could hypothesize that changing an estimate of fitness may be one of the easiest ways to get people to change, because as soon as you change that estimate of fitness, they no longer perceive that they are on a peak, and that would therefore cause them to perhaps seek out another peak. They can cause us to resist change. Here, once again, we could look at this question of, does having a strong estimate of fitness in mind make us less likely to consider alternative behaviors from the ones that we're engaging in? They provide us a means of comparison with others. We talked about college rankings. CEOs have been accused of basing their salary on what other CEO salaries are, not because they necessarily are worth it, but because if they're making less than the other person, then they're perceived as being less valuable. So estimates of fitness, once again, play an important role in this. And maybe the question of what estimates of fitness are rational and what estimates of fitness really aren't that rational. And as I pointed out in the university context, in terms of determining the fitness of a university for a particular student, estimates like the U.S. News and World Report don't seem to be particularly useful. Is there a difference in value between rational and irrational estimates of fitness, and how do you distinguish between the two? These are all the types of research questions that a conceptual framework like the one that I just presented could be used to address.